I now would like to test some of the results that we have here, that we have worked out here. I'm going to shoot a pellet, a metal ball. I'm going to shoot it at various angles. 30 degrees, 60 degrees, 45 degrees. And I'm going to make a prediction, if I shoot it up from there, where it will hit the table. A measurement is meaningless without knowing the uncertainties. The first thing I want to know is what is the velocity of this bullet when it comes out of the spring? And does it vary if I do it 3, 5, 6 times in a row? It's not a $20,000 spring gun, so it is likely to vary. And the way I'm going to do that is as follows. If I shoot an object vertically up, that is the maximum value that it can go. So when alpha equals 90 degrees, then the sine of alpha is 1, then the height is V0 squared divided by 2g. G. In other words, if I measure the height, if I shoot it up vertically, and you can measure that for me, you will see how I'm asking you to do that, then we can calculate V0 squared. So the first thing I want to do is to shoot it up vertically, and how are you going to help me to tell me how high it is? That comes easier than you think. The top part of this stick is 3 meters, the top mark. That very top mark is 3 meters. And all I want you to tell me whether it is yay much above or yay much below. And then we'll estimate that yay much, and then we'll make a guess. And I'll do it twice. So if you're ready, make sure that you can distinguish between above and below. Makes a big difference. Yeah? Okay? 3, 2, 1, 0. Okay, was it higher or lower? How much? This much? Do we agree? Let's say 5 centimeters, right? We're going to allow for an uncertainty. I'll do it again. I want to see how well it reproduces. 3, 2, 1, 0. Okay, was it higher or lower? How much? This much? Do we agree? Let's say 5 centimeters, right? We're going to allow for an uncertainty. I'll do it again. I want to see how well it reproduces. 3, 2, 1, 0. Lower. Higher. So it was 10 centimeters, 5 centimeters higher, so we'll take 7. So we will make 7 and we'll have to allow for an uncertainty. So H max is about 3.07. I have done this morning 20 times. And there were times that the height differed by more than 10 centimeters, sometimes even 15 centimeters. I therefore would feel most comfortable if you allow me an uncertainty of 15 centimeters in that height. This is a 5% error. 5%. So what now is V0 squared? Well, that's easy to calculate now. Now I'm going to set the angle at 45 degrees. But how accurately can I do that? I don't think I can do that any better than 1 degree. I'll try to do the best I can, but I can't really guarantee you that I'm accurate to 1 degree. So now comes the question, what happens with the sign of 2 alpha? Because we're going to measure OS. What happens with the sign of 2 alpha? The sign of 90 degrees is 1.0000. But what would be the sign of 88 degrees? That is the value that I cannot exclude if I'm off by 1 degree. And that value is 0.9994. That is so close to 1 that it is only off by 0.6%. 0.06%. And that is so low compared to 5%, forget it. Forget the error in alpha. This is my prediction for an angle of 45 degrees. This will only hold if there is no air drag, or if the air drag is negligible, and of course, equally important, that that spring gun, when the ball comes out, that the velocity square is indeed within the range that we have assumed, and that it doesn't have bad days and good days. There's no way I can check that anymore. All right? So we're going to mark the 0.614. This is 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter, 6.14. 14 centimeters. My God, it's all the way here. And then I allow for an error of about 30 centimeters. Did I do that right? That is correct. 45 degrees, a 30 centimeter uncertainty. That is all the way up to here. And then the next one, roughly 30 centimeters. So that's where, if our calculations make sense, that's where the ball should hit. Now I would like you to come here, if you don't mind, and stand here. And the moment that that ball hits, point your finger at it. 3, 2, 1, 0. Put your finger there. Isn't that fantastic? Isn't that amazing? Do you see now how important it is that you have uncertainties in your measurement? In high school you would have said it has to hit there. Bull, man. It has an error. And the error has to be taken into account. Whereas so now, I wonder what happens if I fire the ball at 30 degrees. Well, if I do it at 30 degrees, then my V0 square is the same. I don't have to worry about that, I hope. However, I cannot be certain about the angle to better than 1 degree. And I find 5.31 plus or minus. Now, 2% error in the sign of 2 alpha, 5% error in V0 squared, that gives me, I can't help it, a 7% error. So I have a 7% uncertainty multiplied by 0.07, so I cannot trust this any better than 37 centimeters. And so now I'm going to put the markers out at 5 meters and 31 centimeters. This is the 5 meter mark, 31 centimeters. And I allow for 37 centimeters on either side. It's here. And 37 centimeters on this side, that is here. Stay here, stay out of the fire line. And when that ball hits, you jump on it. Yeah, you jump on it. And now I have to change the angle to 30 degrees. Okay, it's as close as I can do it. Okay, you ready? You are? 3, 2, 1. Ah! Hit the jackpot! If you allow for an uncertainty of 1 degree on either side, you will find exactly these same numbers because of the symmetry of the sine curve. So again, you're off by 2%. No difference. And so this prediction is unchanged. So I don't have to change these markers. They're all perfect, provided that nature is willing to reproduce itself. 60 degrees. Ready? 3, 2, 1, 0. Here, man. Yeah, here, right? Thank you very much. Wonderful. Look. Maybe my uncertainties were not so dumb. We were just lucky here with the jackpot. It's comfortably within the error, but close to this one. So I'm quite happy that I took the uncertainties the way I did.